on chemical kinetics. This is lecture number 12. We have been on this for the past 11 lectures. So, just quickly to remind you of what we were doing in the last class. So, we had talked about this one very briefly, where we said that this is the kinetic energy distribution, right, of molecules, say in gas phase in a reaction vessel, and these are the fraction of molecules having the respective kinetic energy as plotted on the x axis. The main point for a particular distribution is that not all molecules will be having the same kinetic energy. There is a distribution of kinetic energies. Then at each temperature the kinetic energy peaks at a certain value, and this value where it peaks, this value we say is the most probable kinetic energy. Now, how do we bring it or relate it to the activation energy? So, we say that suppose we take two different temperatures, 300 Kelvin and 900 Kelvin, just as examples. So, what happens is when you increase the temperature to 900 Kelvin, two things happen. One is, see this black curve, this is at higher temperature, it has become broader. Broader means that you have more molecules with higher kinetic energies, right, and the value of the most probable kinetic energy has also gone up. That means the value has increased as compared to that at 300 Kelvin. Now, suppose you say that okay, at this point this is the EA, the activation energy, that means the energy it needs to go over the energy over the barrier and to the product side. So, the energy the reactant molecules would need to go to the top of the hill, which is the barrier, and then the top of the barrier and go over to the product side. So, if you say that this is EA and you say that EA is constant, right, and you just draw a vertical line parallel to the y axis. So, what you see is at the lower temperature is 300 Kelvin, this blue shaded region is the one which tells you that these are the fraction of molecules having energy in excess of EA. If these fraction of molecules are having energy in excess of EA, then what is going to happen? These fraction of molecules are going to readily go over to the product side, because they already have the energy which is close to EA or more. Now, what happens when you increase the temperature is, as this pictorially tells you, or in terms of figure it tells you in terms of a diagram. See, when I increase it to 900 Kelvin, now you look at this black curve, the black curve now is shifted, that means it shifted above, that means there is more area under the black curve above EA. So, the area what is, so if you look at the area, that means the fraction of molecules for the black curve, that is the curve at 900 Kelvin, what you would understand that there are more molecules, many more molecules as compared to that at 300 Kelvin. So, that means you have more molecules which have higher energy, more than the energy of activation, right, at least as much of energy of activation or more than the energy of activation. So, at 900 Kelvin the fraction of molecules having energy higher than the energy of activation is more than the fraction of molecules having energy higher than the energy of activation at 300 Kelvin, as is available from the shaded regions. So, for 900 Kelvin the shaded region would be the green one plus the blue one, while for at 300 Kelvin the shaded region would be only the blue one, right, and this directly tells you what happens when I increase the temperature, right. Hence, going back to again what we wrote, we said that the area of the shaded portion, right, increases as the temperature is increased, right. So, the area of the shaded portion increases as the temperature is increased. Then what we had already mentioned, as the temperature was increased the distribution became broader and the peak of the distribution shifted to higher values of kinetic energy. So, this we had already mentioned. So, now what I just told you was that the fraction of molecules having energy excess, that means over and above that of EA, is given by e to the minus EA over RT, and then this relates you to the Arrhenius's expression for the temperature dependence of reaction rates, which says K is equal to A e to the minus EA by RT. So, then what is this factor telling you? This factor, the exponential factor tells you is what fraction of molecules would be having energy in excess of EA, so that they can easily pass on to the product side. In other words, higher the temperature, right, more is the shaded portion under the curve, that means more is the number of molecules having energy equal to EA or greater, that means more than that, and hence there is a greater chance of the reaction happening, that means the reaction happens faster at higher temperature. And this was the idea behind the discussion of this distribution of energies, as a function of temperature, and seeing how the shape of the distribution changes as I change my temperature, that means go from a lower temperature to a higher temperature, and what it leads to, right. Okay. So, now let us look at our kinetic this Arrhenius expression a little more closely. So, remember, so this was K A minus E A over R T. So, this was our rate expression. So, I think this was equation number 1, please go and cross check. Now, what you do is trying to look at the details. So, we know what A is, right. So, A, well, we will talk about A later, but before that let us look at the this form, the factor in the exponent. Remember, the factor in the exponent has to be dimensionless, right. So, that means E A over R T has to be a pure number, right, that is no dimension. Is that what it is? So, let us check that out. So, generally E A is expressed in kilojoules per mole, which I can write as, so kilo means 1000 or 10 to the power 3 joule mole inverse, right. I can write it like in that form. What about the denominator now? So, R, let us see R. R is your universal gas constant, it is 8.314 joule Kelvin per mole, right. So, this is R. So, and these are the units, right, and then obviously temperature is having the unit of K, that is Kelvin. Okay. So, now what we know is, we know the units of the denominator of the exponent E A, that is activation energy, and also we know the units of R and T respectively. So, let us quickly do E A by R T in terms of units. So, then E A by R T in terms of units would give us, so E A over R T in terms of units would give us joule per mole, right. I am keeping 1000 aside because 1000 is just 10 to the power 3, right, it is kilojoules, that is why that is the general way of expressing activation energy. Then I have R, which is having the units of joule per mole per Kelvin or per Kelvin per mole, or, and then I have K, right, and the moment I do this, you have understood what has happened. So, the Kelvin gets cancelled out, I am left with this, and then the units also get cancelled out. So, what I am having is, I am having a pure, I am having a pure number. If I am having a pure number, so I am absolutely fine with this expression, because this is the power of the exponent, this has to be dimensionless, that is a pure number, and we just proved that it is indeed a pure number, right. What is the importance of this? Why are we doing this? I could have not done this and just moved on, so that I could have finished off the lecture earlier, but the point is the following. See, A, you do not try to memorize these equations, you have to understand what the equation means, what the equation is trying to tell you. Second, if this is this E A by R T is the power in the exponent, what you immediately keep in mind is that this has to be dimensionless. Now, for some reason, suppose you are you are doing something very hurriedly, you are rushing through, and you write down the expression somewhere where you say that K is equal to A e to the minus E A over R, right, or E A over T, and say you have forgotten, you are wondering whether this equation is right or wrong. immediately what you do is you go and check that whatever I have written, if it is EA by R or if you have written EA by T, then it does not become dimensionless, right, as you have seen. It only becomes dimensionless if I have EA over RT, where RT is in the new denominator and EA is in the numerator expressed in their conventional units, right. This is that's why it also becomes a very important checkpoint for you to see whether you actually have written the equation correctly, or even if you do forget, you would always remember that I need to have a dimensionless power, that means exponent. I need to have a dimensionless unit out there or dimensionless quantity out there, and hence it has to be EA over RT. Now once that is settled, you come back to this equation, it is k is equal to A e to the minus EA over RT. So this A, then what is going to happen, because this e to the minus EA by RT is a pure number, right, A has to be equal to k, the units of, okay. So I can write now then units of A should be equal to units of k, which means if for a first order reaction, so for a first order reaction, remember what was k for a first order reaction, so k was time inverse, right, and this would also be the unit of A, right, for a first order reaction. Then recall what it would be for a second order reaction. So for a second order reaction, so k means the unit of k says liter per mole inverse time inverse, and this again is the unit of k. So again what it means is that because that exponential form, because this exponential form is a pure number, then the units of A will have to be that of the units of k. If for a first order reaction, then A is just the inverse of time. If it is for a second order reaction, then it goes like this and so on. So this is liter per mole per time. So this was about the expression or in terms of the units, just to cross check. Now let us talk about the next part under this temperature dependence, which is determining the Arrhenius parameters. Let us do this. We are determining the Arrhenius parameters. So determining, sorry, this will be I out here. Okay. Again, let us go back to the Arrhenius rate equation. So which is k is equal to A minus EA over RT. Now what I can do is I can take natural logarithm on both sides. So I can say that natural log of k is equal to natural log of A minus natural log e to the minus EA over RT. Okay. So let this be equation number 2. Now see that this equation, it is not a continuation of the previous lecture, because I am talking about the temperature dependence today. I have started with a new set of equation numbers. Okay. Now when I have this, I can write again then that ln k is equal to ln A. So this is log base c anyway. So I can, so this one, sorry, this is plus, this is plus. So this one would become minus EA over RT. Okay. Or so go over to the next page. Natural log of k is equal to natural log of A minus EA over RT. Let this be 3. I can also express it in terms of log base 10. So, then it would be 2.303 log base 10 k is equal to 2.303 natural log of a minus E a over R t. See, this would be log a. So, let me write again, it would be 2.303 log 10 k is equal to 2.303 log 10 a minus E a over R t, and then what I can do is I can write log k, which is log base 10 k, is equal to log a, which is log base 10 a, minus E a by 2.303 R t. Okay. So, what have I done is I have replaced this ln k over by log base 10. So, this is the conversion factor. Then I have taken and have divided the equation throughout by 2.303. So, 2.303 gets cancelled, and I have a factor of 2.303 out here, and this is my equation in terms of log base 10. So, this is log base 10. Okay. Again, you look at equation 3 out here. If I write this equation in a little different form, so I can write this like this: natural log of k is equal to minus E a over R t plus a, let this be 4. I just switched the order of the terms, and once I have written this, you immediately understand this is the equation of a straight line. If this is the equation of a straight line, what I get is I should be getting a straight line if I plot natural log against 1 by t, and the type of plot should be a linear plot. The type of plot should be a linear plot. Okay. So, let us see what we get out here. So, what we get is here in terms of a plot, so let this be the plot, right. So, here what I have is I have natural log of k, and here I will be having 1 by t, that is the inverse of temperature. Okay, so, the moment I have this, say these are my experimental points at certain temperatures, right, and I get a straight line through the experimental points. So, this, remember what the equation was, right? The equation was, let me write the equation again. The equation was natural log of k is equal to a minus E a over R t, which we rewrote as ln k is equal to minus E a over R t plus ln a, right. And what we are doing is you are plotting ln k against 1 by t. So, then what is the intercept? The intercept is natural log of a, and what about the slope now? The slope is equal to minus E a over R, right. This form of the Arrhenius equation tells you what is how you can calculate the Arrhenius parameters. So, what are the parameters? The parameters are a, the exponential rate constant, right. Sorry, a is the p exponential factor, there is the Arrhenius factor, and then E a, which is the activation energy. How do you do it? So, what you do is that, see, these different points correspond to different temperatures. So, different 1 by t values, because these are different 1 by t values. So, what essentially doing is that, suppose you have taken a reaction, right, you have taken a reaction, you are not changing anything in the reaction, but the only thing you are changing is the temperature. See, let us take a temperature of 300 Kelvin, right. when we take the temperature to Kelvin, say you start the reaction with an initial concentration of say 1 mole per liter. Okay. Now, if you now raise the temperature, you raise the temperature to whatever, say from 300 to say 320 Kelvin, but everything else remains the same. You cannot change anything else, because you know that rates also depend upon what, the concentrations. So, the initial the concentration remains the same, the only thing you vary is the temperature. So, once you vary the temperature, what you do is you then go to different temperatures, say 320 Kelvin, 340 Kelvin, 360 Kelvin, so on, as the reaction would permit, right. And based on this you generate these points 1 by T. So, at respective temperatures what you do is you have the corresponding rate constants. Okay. So, once you have the rate constants, right, from the rates of the equation, once you have the rate constants, then you are plotting this natural log of the rate constant versus 1 by T, and from this and from the Arrhenius equation which you already know, you are getting the natural log of A as the intercept, from which you get A by doing an anti-log, and the slope it gives you minus EA over R. So, this is how you determine the Arrhenius parameters by any reaction you are working on, or you are focusing on, or you are studying in the lab, right. I hope now it is clear to you the significance of the Arrhenius rate equation, right, especially of that the exponential minus E over RT, that E over RT factor, and also given a reaction how you can design your experiment to figure out the Arrhenius parameters A, which is the pre-exponential factor or the frequency factor, and then the EA, which is the activation energy. Okay. One big assumption out here has been, if you would notice, that see I have done this over a range of temperatures, right, and I have said that the only thing you change is temperature, you do not change anything else in the reaction. This is extremely important, but there is one very clear assumption out here. The assumption is that, so if we write what the assumption is, that A, which is the Arrhenius factor, and EA, which is the activation energy, are independent of temperature. Okay. That means A and EA are constants over the temperature range you have studied. So, if your temperature range goes from say 300 Kelvin or say 280 Kelvin to 400 Kelvin, then when you are doing this plot, your assumption is that the Arrhenius factor A, which is this, and the activation energy EA, they are constant. That means they are not changing with the change in temperature, right. So, having now made this point clear, and again to show you this is the plot you are looking at, let us move on to this significance of the activation energy. What does this activation energy tell you in terms of its magnitude? So, let us talk about the magnitude of activation energy EA. Okay. Let us talk about this, right. Now, what does EA tell you? Let us go through few equations and then we will understand what EA is telling us. But to start with, just let me mention, because this was the slope, right, this was the plot of ln k versus 1 by t. What the inherent message you get from here is the slope is equal to minus EA over R. R is a constant, so the slope is going to depend upon the activation energy EA, right. Hence, the slope will depend upon this EA. Now obviously depending upon EA the slope will change, either the slope will increase or the slope will decrease, right. If that happens, it tells you, that means EA, the activation energy, tells you how sensitive a particular reaction is to the temperature. That means when you change the temperature, this slope or EA will determine the degree to which the rate of reaction will be affected. So let me write that down, but before I do that I forgot to write here one thing. So this plot is referred to as the Arrhenius plot, right, just something I thought I would mention. But anyway, so what I was saying was that then EA for a particular reaction, the magnitude of the activation energy EA will determine or tell you the degree to which the rate of reaction is increased under similar concentration conditions when the temperature is increased, okay, when the temperature is increased. So again let us go through this. So what does the magnitude of EA tell you? So the magnitude of EA will determine the degree to which the rate of reaction is increased, if I put a comma out here, under similar concentration conditions. So this is extremely important, under similar concentration conditions, that means you are not changing the concentrations, right, you cannot change everything because rates also depend upon concentrations, right. So then they determine the degree to which the rate of reaction is increased under similar concentration conditions when the temperature is increased. So this is what the magnitude of EA tries to deliver to you, the message it tries to deliver, okay. So can we look at some mathematical interpretation of the same. So what we will do is, again we will start with our equation K is equal to A minus EA over RT. So this was equation 1. Now let us take two temperatures, okay, let us take two temperatures. So two temperatures are T1 and T2, and it is given so both the temperatures are in Kelvin, remember always temperatures are in Kelvin, please take temperature in Kelvin, do not by mistake put in degree Celsius, please, no. So T1 and T2, then I say that T2 is greater than T1, okay. So T2 is higher than T1, that means T2 is telling you that it is a higher temperature than T1, you are running the reaction at a higher temperature, okay. Now let us come back and look at one. So what I will do is, for T1 the rate constant will be referred to as K1, and for T2 the rate constant will be referred to as K2. So what I can say is that here for T1 the rate constant is K1, for T2 the rate constant is K2, okay. Once that is clear, let me write down the expressions. So I have then, based on Arrhenius' equation, natural log K1 is equal to natural log A, right, minus E A over R T 1. Let this be 5. Next, natural log of K 2, which is the rate constant at temperature T 2, is equal to A minus E A over R T 2. This is 6. Again, please see that both ln A and E A have been kept the same. We have not changed that. Two things are changing. One is the rate constant, and obviously the other one is the temperature, right. So, again assumptions, the same assumptions, remember, A and E A are constant. Okay. So, this is a assumption. So, then what you can do is, now I will subtract equation 5 from equation 6. So, then I can write 6 minus 5, equation 6 minus equation 5 will give me natural log K 2 minus natural log K 1 is equal to ln A minus E A over R T 2 minus ln A minus E A over R T 1. Okay, so these are R T 1. So, ln A minus E over R T 2. So, this is R ln A minus E over R T 1 again. So, once we have this, so you can immediately realize that ln A will cancel out. Why? Because A is a constant anyway, did not change in temperature, and then E A is also constant, it is independent of temperature, we said assumption. R obviously is constant. Okay, so, then we can write that natural log of K 2 over K 1 is equal to E A over R 1 by T 1 minus 1 by T 2. Okay. So, this is a very important expression, or this is a very important equation. What is it telling you? It is telling you that depending upon what your temperatures are, with the assumption that the Arrhenius factor A and the activation energy E A are constant, it will tell you, that means the activation energy will tell you to what extent K 1 and K 2 would vary. That means to what extent K 1 would increase to K 2 if the temperature is increased from T 1 to T 2, and we can easily find this if we know what the activation energy is for the specific reaction. Hence, you go back to our initial statement, that means the magnitude of the activation energy. What did we say? We said that the magnitude of E A will determine the degree, that means the extent to which the rate of the reaction is increased when the temperature is increased, but make sure that concentration conditions are kept the same. Okay. So, this was about the magnitude of the activation energy. So, now I will close this discussion on the temperature dependence of reaction rates by just looking at this final thing. Let us talk about a reaction which has the rate expression R is equal to K, that means the rate law, A to the power alpha, B to the power beta, and for this what I can write is K follows A minus E A over R T, and we know that from the Arrhenius equation. But think about this at a given temperature. So, that means at a given temperature, if I look at this equation, then I can say the reaction rate, okay, will depend upon. So, I look at this and I also look at this rate law, will depend upon 1. What will it depend upon? It will depend upon A, which is the Arrhenius factor, which is this, okay. It will depend upon magnitude of EA, the activation energy. Also based on this, the rate law, it will depend upon what? It will depend upon the initial concentration of the reactants, right. It will depend upon the initial concentration of the reactants, which are A naught and B naught, because these are the initial concentrations. After that, depending upon the reaction, A naught and B naught will start decreasing. So, you understand that at the initial conditions, as we had discussed before, you will anyway be having the maximum rate. So, that is why you say it will depend on the initial conditions. But now we are talking about a fixed temperature. See, we are talking about a fixed temperature at a given temperature. So, if you are talking about a given temperature now, so temperature is out of the equation, right, because temperature is constant. So, what it is depending upon? It is depending upon A, which is the frequency factor or Arrhenius factor or the pre-exponential factor, then EA, which is what? The activation energy or the magnitude of the activation energy, and then also upon the initial concentrations of A and B. Okay. Then the question that comes to your mind is, which one is more dominant, isn't it? That is the logical thing, because if it is depend upon all these 3, then which one would be more dominant? So, then you pose the question, what you pose the question is, the question you pose is that which of these factors will influence or affect the reaction rate more, or which one will be the most influential one. Let us look at a small table to find out the answer for this. Now, follow the table carefully. So, just let me give me some time to write the table down, then I can explain the same to you. So, what I am doing is, so let us this be EA, the activation energy given in kilojoule per mole. Okay. Then what I am writing in the table is exponential minus EA over RT. Okay. So, I am calculating this factor. What is this factor? Remember, this factor is the factor which was written out here, e to the minus EA by RT. So, I am writing is exponential minus EA by RT. Okay. And what I am doing is, I am calculating it. Say if I draw a line out here, and if I draw another line out here, I am calculating for 2 different temperatures. What are the temperatures? One is T is equal to 300 Kelvin, and the other one is T is equal to 600 Kelvin. Okay. So, these are my 2 different temperatures. Okay. So, let us go ahead and complete the table. Okay. Now let us write down the values. So what are you doing out here again? So what you are doing is you are having different activation energies which I will put in right now. Say for I will put in 3 values. One activation energy is 11.5 kilojoule per mole. Once you are given this activation energy, once you know this temperature, right, I can easily calculate minus exponential minus E over RT. So that is 10 to the power minus 2 at 300 Kelvin. When I go to 600 Kelvin, it becomes 10 to the power minus 1. Okay. Let us take another EA activation energy which is 51.7. Here it is 10 to the power minus 9 and here it is 3.2 times 10 to the power minus 5. Okay. And one more 103.4 kilojoule per mole is the activation energy now. In this case it is 10 to the power minus 18 and this is 10 to the power minus 9. Okay. So again what have you done is, if I draw these lines in between to make it a little more clear. So I have taken 3 activation energies, I have 2 temperatures 300 and 600 Kelvin, right. Then I say that for a given activation energy I am calculating this exponential factor exponential minus E over RT, where I know EA from here and I know T from here. So at 300 Kelvin for 11.5 it is 10 to the minus 2, at 300 Kelvin for 51.7 being the activation energy is 10 to the minus 9, then at 300 Kelvin for 103.4 kilojoule per mole being the activation energy is 10 to the minus 18. You go to 600 Kelvin now for the same EA values 11.5 it gives 10 to the minus 1, 51.7 it gives 3.2 times 10 to the minus 5, at 103.4 it gives 10 to the minus 9. Okay. So you have this table in front of you. Now look at, let us take example the 300 Kelvin table which is this one, the 300 Kelvin. So see what has happened. At 11.5 the exponential factor is 10 to the minus 2. The moment you increase your activation energy by close to 10 times, it is not exactly 10 times, 10 times would have been 115, but this is close, so 103.4, you see the extent to which this exponential factor has changed. It has gone from 10 to the minus 2 to 10 to the minus 18. Okay. So let us not consider 10 times even, let us consider close to something as roughly 5 times, that is 11.5 to 51.7 at 300 Kelvin. What has happened? I go from a value of 10 to the minus 2 for this exponential factor to a value of 10 to the minus 9. So realize now for a 10 times change, so a factor of 10 change, the activation energy changes by so many orders of magnitude. Do you think that concentration or even the other factor which is A would be able to keep up? No. So then the bottom line is that if I write it again, at 300 Kelvin, which is very close to room temperature. So when we say room temperature, we are saying 300 minus 273, which is about 27 degrees Celsius. Okay, at 300 Kelvin, which is very close to room temperature, that is the traditional room temperature that we take. A change in EA by by a factor of approximately 10 leads to an enormous change leads to an enormous change in the exponential term covering over 16 orders of magnitude. So, here the enormous change just by a factor of 10 leads to an enormous change, and what is the enormous change? It is 16 orders of magnitude. Okay. Let us revisit the table. This is what we are talking about. At 11.5 it is 10 to the minus 2, I go to 1 to the 3.4 it is 10 to the power minus 18, 10 to the minus 2 to the minus 18 factor of 10 to the minus 16, that is the change I am looking at just by a simple change in EA by a factor of 10, because this is such an enormous change. Thus, within the temperature range, just within the temperature range which we have said 300 to 600 Kelvin, it is generally valid to compare rates of different reactions, solely on the basis of their values of activation energy, solely based on the values of activation energy, right. And this why? Because any effects due to changes in concentration, or A, the pre-exponential factor, are virtually swamped out, they are completely masked, okay, are virtually swamped out. I can say solely on the basis of their activation energies. Why? Because these are then their effects are negligible, when the effects of A or concentration are negligible as compared to the influence that EA has on the reaction rate. Now, hopefully having done this discussion, this gives you a better feeling of what this activation energy is telling you in terms of a reaction, a chemical reaction that you might be studying or doing in lab. So, we will come back to this activation energy concept when we talk about elementary reactions, right, that would be a next topic. But before I go to the next topic, what I will do is I will just do a simple example of this related to this Arrhenius equation of on the dependence of temperature of reaction rates, right, and then again reach another general conclusion, as you will see. So, the problem is, or example is, you are having cyclobutene in the gas phase, these are hydrogens, okay. Obviously, these corners are your carbon atoms, and then you have a hydrogen out here, you have a hydrogen out here, okay. Then the gas phase, in the gas phase, okay. So, this goes to butadiene, H2C double bond CH, CH double bond CH, right. So, you have butadiene out here, and here you have cyclobutene. What you are told, is that the activation energy EA for this reaction is 137 kilojoule per mole. What you are also told is, or what you are being asked now, if I change temperature from 420 Kelvin to 430 Kelvin, that is a 10 K change. There is a 10 K change. By what factor will reaction rate increase? Okay. By what factor will the reaction rate increase? So, it is a very easy straightforward question. I have changed the temperature from 420 to 430 Kelvin for this transformation of cyclobutene to butadiene in the gas phase. Okay. The activation energy is given as 137 kilojoules per mole. Please work it out. Next class I will start with this and then move on to elementary reactions. Okay. Thank you.